Please title these notes Application Date. By the end of this lesson you should be. So let's jump right into some problems. The length of the side of a cube is increasing of 4 meters per second. In terms of the surface area, let's call that A of the cube, what is the rate of change in meters cubed per second? Okay, so let's draw our diagram. We've got a cube. It has some side length S. The length of the side is increasing at a constant rate, so side rate, that's ds dt. What is the rate of change of the volume? So that's dv dt, okay? So we want some equation relating volume to side length. So this is just a cubed, so length times width times height, those are all s. So that means that volume equals side cubed. And we're dealing with rates, so we can do the same thing we've always done. Take the derivative with respect to t. Okay, so here we've got our little equation, but the thing is that right here it says we want the dv dt to be in terms of area, surface area, excuse me. And so we don't have any numbers to plug in here like we normally would. No s, no dt, none of that. All that we have is a formula for surface area. So surface area of a cube, let's see, if we take a cube, imagine like a dice or something, or a die, it has 6 faces, and each of those faces is a square. So the area of one face is s squared. So the area of all 6 faces is 6s squared. So that means the surface area is 6s squared. Here, because we're writing it in terms of A, so we're not going to take the derivative. ds dt does equal 4 here. So we can do a little bit more with this. Now, notice right here, this 12s squared. This is really similar to 6s squared. In fact, if we multiply this whole thing by 2, oops, this is 6, I'm getting ahead of myself. Notice how this matches up with this. So whenever we have two things that match up exactly, we can substitute. Take out the 12s squared, put in the 2a. We're told our units are meters cubed per second. So what this allows us to do is it allows us to say we don't have to know the side length anymore. If we know the surface area, then that will be enough to help us figure out dV/dt. And this is useful if there's some other quantity that is more easily knowable than what would normally show up in the problem. And so this is just another type of problem that you can see. Okay, here's another type of problem. The radius of a cylinder is increasing while the height stays a constant 6 centimeters. At a certain instant, the rate of increase of the volume of the cylinder is numerically equal. That just means the numbers are the same even if the units aren't the same, to twice the rate of increase of the surface area What is the radius of the cylinder at that instant? Okay, let's find some rates. So at a certain instant, the rate of increase of the volume, so this is dV/dt, numerically equal to twice the rate of increase of the surface area. So let's use A again, dA dt. What is the radius? Okay, so let's draw a little picture. We've got a cylinder. It has R. We know the radius of the cylinder is increasing, so that should be a variable. The height is a constant 6 centimeters, so that's just 6. So now we need a couple of equations. We've got area and volume. We don't have an equation directly relating the two of them, but let's write them both out in terms of the radius, because the radius is also in the problem, and let's see what happens. So we know that the volume of a cylinder is the area of the base times height. So the area of the base is pi r squared times the height, which is 6. Okay. And then the surface area, that's going to be 2 area of the base. Basically, there's one circle on top, there's one circle down here on the bottom. So if we find the area of each of these circles, there are 2 of them, that'll give us part of the surface area. And then we also have basically this tube that's forming the height. So we imagine that as if we had a little cylinder or whatever, something like this. And this top width, this distance, notice, is the circumference of that top circle. And this height is the same as the height here. So the circumference of the circle times height. So this is 2. The area of the base is pi r squared. Circumference is 2 pi r. And height is 6. So let's take our derivatives and see what happens. The 6 and the pi are just along for the ride. Two and the pi are along for the ride. Twelve pi is along for the ride. Okay. Let's see, dt is 12 pi r. Two equations, which is a little too much. So let's come back and look at what we're solving for. So we actually want to find the radius, so somehow we've got to get down to one equation with just an r in it. And we know that the dv dt is twice dA dt. So dv dt equals 2 dA dt. So we can at least take that out and sort of plug it in here. 2 dA dt equals 12 pi r. Times dr dt. Let's see where that gets us. Well, notice that we've got a dA dt over here and a dA dt over here. So that means that we can substitute all of this right into here if we like. That gets rid of another variable. So we've got 2 times 4 pi r dr dt plus 12 pi dr dt r dt. Okay, so now we're down to just dr dt and an r, which is getting better. Let's distribute this 2, just to make life simpler. 8 pi r dr dt plus 24 pi dr dt equals 12 pi r dr dt. Now, one of the things that I noticed looking at this is that every single term has a pi and a dr dt. So that means we can divide everything by pi dr dt. Oops. Presuming dr dt is not 0, which if the volume and surface area are changing, it can't be. So now we've got 8r plus 24 equals 12r, which makes life significantly simpler. Subtract 8r from both sides. Divide by 4. And the units are in centimeters. Okay, let's do a third type of problem. The height of a rectangle is increasing at 3 meters per second, and the length is decreasing at 2 meters per second. Under what conditions is the area of the rectangle increasing? Is increasing, so we're talking about dH dt. Length is decreasing. That means we're talking about dl dt. We're talking about area increasing, so we're talking about dA dt. So we want something relating h, l, and a, and that's easy enough to do. If we've just got a little rectangle, area is length times height. And furthermore, we can just write area as, so we're going to deal with these rates, so let's do our derivatives. Notice this is a product rule, so that means derivative of L with respect to t times h plus L times derivative of h with respect to t, just like that. At dh dt is 3 meters per second. dl dt is decreasing, so it's negative. It's negative 2 meters per second. And we know that area is increasing, so that means that dA dt must be greater than 0. Because an increasing rate, that means a positive derivative. So that means 2h plus L times 3, that's going to give us our dA dt. We know that all of that has to be greater than 0. So now, if we want to figure out under what conditions is the area of the rectangle increasing, all we basically have to do is solve for one of these variables. We aren't going to be able to get these variables worked out any further and define actual numbers, but what this is basically saying is it's saying that for a certain relationship between h and L, if that relationship is true, then the area of the rectangle is increasing. So let's add 2h to both sides. We can divide either way. Let's go ahead and divide both sides by 2. So what this really means is that when h is less than 3/2 L, the area of the rectangle is decreasing because, increasing. Because dA dt is greater than 0. Finally, let's do a check for if the area of a rectangle stays a constant 12 square meters, what is the rate of change of the length when the rate of change of the height is 0.2 meters per second and the height is 3 meters. Go ahead and try that one on your own. Pause the video and then restart the video when you're ready. Pause the video now. Okay, rate of change of length, that's dl dt. rate of change of height, that's dh dt. So we want something relating h and l. We know we have a little rectangle. So we're dealing with area up here, so we know that area equals length times height. And the area is always 12 meters squared. This is a constant, so when we take the derivative of it, that's always going to be 0. We can just put in the 12 right now. Derivative of 12 is 0. Doing the product rule, so the derivative of L with respect to t times h plus L times the derivative of h with respect to t. Furthermore, we are told that dh dt is 0.2 and that h equals 3. So we are solving for what is the rate of change of the length, dl dt. So that means we should start doing some substitution over here. dl dt is our unknown, h is 3, L we don't know, dh dt is 0.2. So that means we need to find L. We do know that 12 equals L times h. We know that h equals 3. So that means that L equals 4. So we can subtract 0.8 from both sides. Divide by 3. Approximately negative 0.26 repeating meters per second. You do that in the calculator. That concludes these notes.